Sonja Wogrin.
You pronounce that perfectly.
Yeah, great. And from the University of Comillas in Madrid, who will be giving this morning's keynote talk.
Thank you very much. Thank you, Chris. Thank you, Andy, for inviting me to give a talk here. It's a great honor for me to be able to talk to you all. The topic of my talk is going to be challenges and status quo of hierarchical optimization and equilibrium problems in power systems. And just to start, I thought I would sneak in a slide about me, because on the timetable it kind of seems like I'm currently unemployed, because it says that my affiliation is none or other. I don't know what I did wrong there. But I actually have a job. I'm an associate professor at Comillas Pontifical University in Madrid. I have several research interests in energy, bi-level programming, investment, storage. I'm originally, actually, so I'm confessing here now, I'm originally a mathematician that got corrupted by power engineers into doing very interesting problems. Happily corrupted, I have to say. And I'm Austrian, so that's why I put a picture of me skiing up there. I work on a couple of different topics. For example, one of the topics I'm working on is how thermal fatigue impacts optimal operations of a combined cycle unit. So whether taking into account the additional cost incurred by thermal fatigue in a power plant would actually change the way that we're operating these combined cycles or not. And in general, this information on fatigue is not something that we know in real time, usually. I work in improving mid and long-term models in the power sector, and that is also related in particular to my current or recent research interest, which is storage and everything related to storage, operation, and allocation. And in the past, and especially during my PhD, I was working on bi-level programming. Even though my last publication in bi-level programming is a couple years in the past, I thought, since at Isaac Newton Institute we would like to encourage, what are challenges, what can I ask of really smart people to do in the future, what does bi-level programming need? So this is a more tutorial talk of what I think is the status quo in bi-level programming, and what I would ask you all smart people to develop in the future so that these methods get even more efficient. Okay, a brief outline of my talk. I'll give a quick introduction. I'll talk about what, up to my knowledge, are the current techniques that are being used to solve these bi-level programming problems right now. Then I'll mention two applications in power systems and discuss what I think is the gap in the literature in those problems, and then have a couple of conclusions. Okay, so ever since the power sector has been liberalized for the mathematicians and for people who like game theory, that was a wonderful thing to happen, because now, as opposed to a centralized planner, we have all of these individual private entities who take decisions gaming with each other. And some of these games are sequential games that could be viewed as some Stackelberg type game. Now, if you're facing a sequential decision-making process like a Stackelberg type game, then this brings us into the realm of what I'm calling hierarchical or bi-level optimization and equilibrium problems. We've actually seen one of those yesterday. Remtin is not here yet, but Remtin yesterday talked about a merchant storage investor, which actually was a bi-level program. So I'll also talk about the applications of strategic storage investment and transmission expansion in comparison in the topic of bi-level programming. So now very briefly and generally, a bi-level program essentially is an optimization problem that has another optimization problem within its constraints. Okay? Some specific other things that you might have heard already, for example, yesterday, are MPECs, so mathematical problems with equilibrium constraints. So an optimization problem that has some conditions that represent an equilibrium problem within its constraints. And an EPAC, an equilibrium problem with equilibrium constraints, so where you essentially have several different entities or agents facing an MPEC at the same time. And now to very briefly and with the minimum use of equations show you this, because I'm sure most of you already know what bi-level programming is, I wanted to motivate all of this with a very simple example of generation expansion planning, because that's where I did my PhD and that's where all of my bi-level intuition essentially comes from. So think about two identical firms or several identical firms with a perfectly substitutable product, and they're either facing a one-stage or a two-stage game. Okay? So a one-stage game and a two-stage game. In the one-stage game, these players decide their investment and their production decisions at the same time, as if you were building a power plant, and while you were building it, you were already producing energy with it. Okay? So it's a simplification of reality. Whereas in a two-stage framework, a bi-level framework, or a closed-loop framework, whatever the nomenclature that you prefer, there we have first investment decisions, and once these are taken, then in the second stage we have a market equilibrium that determines what the productions with this energy would be. Okay, so very, very simple math. If we have the single level equilibrium, think of different firms maximizing their total profits, and they're both deciding their capacities X and their quantities Q at the same time. And then there are some market clearing conditions that tie all of these optimization problems together. You solve that. If you would like to look at this conceptually, mathematically speaking, you could take the KKT conditions of each of these individual companies' optimization problem, profit maximization problem. You end up with a set of nonlinear equations of KKT conditions, and you can solve that numerically. Okay, so that would be the single level problem. Now when we go to something bi-level, okay, then we actually separate when we make the decision of investment versus quantity. Okay, so here we say in our upper level we're still maximizing our total profits, but we're only deciding our capacity X, as opposed to before we were deciding X and Q at the same time. So now we're deciding X subject to the lower level, which in itself is an equilibrium problem where people actually maximize their market profits altogether. Okay, so that would be an MPEG. So that's one strategic merchant investor or one strategic generation expansion company that would decide its capacity subject to what happens in the market. If several generation companies or merchant investors, as said Ramtin yesterday, are facing this type of problem at the same time, then we get to something that's an EPEC, right? So an equilibrium problem with equilibrium constraints. And conceptually speaking, you could think of this as having an equilibrium on the upper level and an equilibrium on the lower level. Okay? Right, but that's now just a very brief introduction to get a little bit of a feel of what these methods are. So I have looked at the recent literature, and I'm not claiming that what I'm saying here is exhaustive. So if you think that there is something that is missing, if you have a method to solve these problems that I'm not aware of, then please pop me an email. I would love to take this into account. But so far, this is what I've come up with. So I've tried to separate these solution methods into solution methods for MPECs and EPECs. Okay, so for optimization, bi-level optimization problems, A, and bi-level equilibrium problems, B. Okay? And there are several different methods for each of those. Let me start with discussing a little bit the methods that I saw out there for bi-level optimization problems. So in a recent PhD thesis that I've attended in Copenhagen just a couple of months ago, they brought up a very interesting parametric programming method that I wasn't aware of, that I thought might have potential for the future. There are methods called single level reductions, where we essentially replace this lower level by its KKT conditions or some equivalent, and then we solve one single optimization problem. There are other methods that enumerate different heuristic optimization methods, so descent, penalty, trust region, evolutionary algorithms, etc. And then finally, I snuck in a new category which I would like to call computationally efficient solution or approximation methods for this. Okay, so this is where it gets a little bit more frou-frou, let's say. Right, okay, so parametric programming. Henrik Billing, Stephen Gabriel, and Trine Boomsma have come up with a very, very interesting, ingenious method of coping with linear bilevel problems or bilevel problems that have bilinear terms in the objective functions. So with their method, they can solve these bilinear or linear bilevel programming problems to global optimality without any kind of discretization, so it's really a global approach. Downside would be, well, if you're something that is not linear or not bilinear, then this method just doesn't work. And currently, it's not available on commercial software because he has just, finished his PhD. Henrik has now started working at IKEA, so I doubt we'll see him soon, anytime, in the bilevel community. And when I was reading the paper, it was not completely clear, and I talked to him and he said he wasn't completely sure either how his method would scale for large-scale problems, because essentially what he was doing is he was parametrizing the upper-level objective function for different optimal bases in the lower level. So imagine that x would be your upper-level objective variable, and on the lower level you have 3 different optimal bases that you could have, and for each of those you can parameterize the upper level objective function in a linear format. So that's very nice, because when things are linear, then they're convex, and then it's easy to find a global solution. And where a little bit of the grain of salt is in that method is, in order to enumerate all of these optimal bases in the lower level, he's using some kind of dual simplex algorithm, and he says that for large-scale problems it's not exactly sure how many of those different bases he has to go through and how that scales. But I thought that the method was very interesting. Okay, what is what most people do, I would say, in my opinion, what most people do is single level reductions. So we replace this lower level by its KKT conditions or by a primal dual formulation, and then we either transform these the nonlinearities of these KKT conditions into a MIP, or we transform everything into a MIP and solve a mixed integer program then, or we leave the MPEG as it is with this non-convexity and solve that directly. Okay. Well, solving this directly as a non-convex problem is something that you don't see in the literature very often, because essentially you cannot argue any global kind of solution. You only get local solutions. So that's, whoops. So that's a downside. If you transform everything into a mixed integer program, then you can actually get a global optimum, which is great. But then by introducing all of these binary variables, there is no free lunch, and then you get very high computational times due to branch and bounds and so on and so forth, and some potential other numerical problems due to the big M's, which I'm sure a lot of you are aware about. And if not, then please read the paper of Pineda and Morales, which has a very catchy title. It's called "Not All That Glitters Is Gold." Big M's, so and so. So I thought that was very interesting. What else is there? Well, enumeration methods. I don't want to go too much into details in all of these methods. I just want to give you an overall assessment of what I think are the pros and cons. So I think that you achieve global optimality, which is of course what we're going for. But then again, computationally speaking, this takes very long. Now, in these heuristic methods that I've seen, I'm not an expert on them, and actually I haven't seen them being applied to problems in power system all that much. So the references that I have here are usually applied to other sectors. And since I'm not an expert, I didn't want to put in writing something that was potentially stupid and wrong. And my PhD supervisor has taught me that never to put anything in writing that you're not sure of, so I didn't. But in general, I think my assessment would be that these problems have the pro of potentially being able to address nasty structurally problems in bi-level problems. So if you have some binary variables in the lower level or something like this, but then it seems that in general they don't really scale very well for large scale applications. That's my general idea that I get for these types of problems. Okay, and in terms of some computationally efficient methods that I've seen out there, there is this one idea by Pineda, Billing, and Morales, which is essentially doing regularization, but estimating your big M constants, coupling this regularization with mixed integer programming, so that you get good estimates for these big M constants, and doing this iteratively. Computationally, that's very efficient. Then I should probably specify this. It's not guaranteed that you get the global optimum, but in a numeric test, we've seen that actually a lot of times you actually do achieve the global optimum. So there is no theoretical proof that this actually gives you the global optimum, but computationally it's quite efficient. I had my PhD student actually use this because we were running into a lot of limitations with our mixed integer problem and could only solve very small problem instances, and this has helped us a lot. Downsides, well, no global optimum is guaranteed, and then again, it only works for linear bi-level problems. So this is a quick chart that I stole from their paper, which is indicating for small, medium, and large case sizes the number of problems where you actually found the global optimum and the corresponding computational time. So I think in practice this is something that works pretty well, even though there is no theoretical proof behind it. So something that you can use in practice. Okay. Bi-level equilibrium problems, EPECs. So there is less out there because the further up you go in the hierarchical ladder, the more difficult it gets to solve these problems. And I have identified, well, diagonalization, single level reductions, and then I wanted to say something about different computationally efficient methods too. So what can you do? You have an EPEC. If you have an MPEC and you write its KKT conditions, right, then you can write your KKT conditions for all of your MPECs, and then essentially what you end up with is a very big set of nonlinear equations and inequalities that represents the stationarity conditions of the EPEC. You could then either solve this as a complementarity problem or as a nonlinear problem, or you could transform this into a mixed integer problem as well. And then there are some other kind of computational things that you could do in order to approximate or solve this type of problems. Now, when you transform this into a mixed integer problem, in general what I've seen is there are two options. Either you're a very smart person, like Carlos Ruiz, Antonio Conejo, and Yves Mears, and then you somehow through magic, or not magic, but intellect, manage to transform this EPEC, which is highly non-convex, into a mixed integer problem without actually having to discretize any of your variables. Then there are, the other humans among us, which actually do have to discretize some of their variables in order to get from the EPEC to a mixed integer program. But then again, if you discretize, then you lose some solutions, right? In general, if in the end you end up with a mixed integer problem, well, mixed integer problems yield global solutions, but then again, to what, right? Because we have stationarity conditions. So if you get if you get an equilibrium out of your EPEC conditions, then that's perfect. But what if you don't? What if you get a saddle point or something else? Then you need to do something about it. And you could also do this as a complementarity problem. Then you're computationally a lot more efficient because you don't have all of these binaries floating around. And we thank Michael Ferris, who is here, for all of these methods, and thank you for giving us the path solver, which has saved us a lot of computational time. There you don't discretize anything, but at least in my experience, for my particular generation expansion planning problem that I wrote as an EPEC, and then as a mixed complementarity problem, for me this worked very badly because I always ended up in infeasible points. And once I ended up in infeasible points, I didn't know what else to do, so I started linearizing things. Okay, so if it finds a solution, then that's of course usually very, very much faster than these mixed integer methods. Okay, diagonalization. We thank Danny for talking about this method in power systems and for bringing us, making this aware. In general, I think I love diagonalization because it makes me solve an EPEC without actually having to solve an EPEC. Right? So it's a kind of fixed point iteration where you iteratively solve MPECs until you converge. So that's great. You only need to solve MPECs. It's very easy to implement. If it converges, you do have an equilibrium. We don't have to worry about these saddle points. But it doesn't necessarily have to find an equilibrium even if it exists. And there may be many different equilibria, and there is, as far as I understand, no way to systematically get these with diagonalization. Okay, some other computationally efficient methods. Well, instead of really solving this problem exactly, you could just, what my husband calls the engineering approach. He works a lot in nuclear power plants, and so he's like, in nuclear power plants, if something doesn't work, they take a big hammer and they just whack on it, which makes me very scared. But he says, well, just do something very brute force, something quick and dirty. And this is a quick and dirty method of solving these EPEC problems with never solving an EPEC, with just solving a single level equilibrium twice, and then approximating what you think would be your bilevel solution. And this is just a quick example from that paper, which essentially shows relative error in investments and in market prices over a different range of strategic market behavior that you could have. Okay, and here we show the difference in error between this approximation scheme that has been proposed and the single level, let's say, naive approach where you just solve a single level problem instead of a bilevel problem where everything is simultaneous. And we see that we're better than this naive approach, but this only works if you're very close to Cournot, and it only works for our specific problem. And so there are very obvious downsides to this method. If you could get a closed form solution of the EPEC, that would be perfect. That's the most efficient thing that you can do from the computational side. So I challenge you all to get closed form solutions for your very complicated large-scale EPECs. That's very hard. You can do this for small problems. Again, Ramtin showed us something about this yesterday. Danny, Ben, Julian, Efraim, and I, we did something like this for, again, a toy problem back in 2013. Computationally, yes, it's efficient, but it doesn't scale for large-scale problems. I will spare you the theorem because we still have a lot of slides to go, and I have to stop at
about quarter two.
Quarter two, okay, good. Okay, so what else is out there? Well, I saw a very interesting column generation method applied to not only a bi-level problem, but a three-level problem, because David Pozo, who is here, is very smart, and he thinks bi-level is for suckers. We do three levels. And so they have a three-level problem where their transmission expansion planner is the first stage, then you have generation expansion on the second stage, and the market on the bottom stage. And they do a column generation method, which essentially, you'll correct me if I'm wrong, gives you the globally optimal solution. It also helps you to study these optimistic and pessimistic points of view from the TAP gap. But if I understand it correctly, you can only do this if the second level variable, so the generation expansion planning variables, is discretizable. Okay, because then you don't take KKT conditions here, you do some Nash equilibrium constraints. Okay. Now this is some of the most efficient things that I've seen for bi-level programs. Okay. So now I would like to talk a little bit about the applications in storage and in transmission and generation expansion planning problem, and where I think the status quo is there in terms of how we model technical things and what is missing and how do we model these. Okay, so there are many bi-level applications in the power system. There is transmission expansion planning, generation expansion planning. There are a lot of different applications in energy storage. There is also applications in strategic bidding, which I'm not going to go into. And there are other sectors for natural gas and plug-in electric vehicles, where you can think of games with aggregators of these vehicles and so on and so forth. Again, many applications, and we don't have time to look at all of them. I'm going to look at one specific problem, which is looking at investment, but in storage. Okay. Now, several different bi-level problems out there. What I've seen other people do on upper level would be you could have a merchant, store, and investor on the upper level taking this investment decision, maximizing profits, or you could have a TSO, or you could have a DSO. You could have demand response aggregators. And what are the different things that they're deciding on these upper levels? Well, they're deciding investment decisions, but not only investment decisions, it's where to put them and how much of them to put, right? So siting and sizing, even optimal bidding of these storage plans, or something related to reliability. So there's really a wide spectrum of different storage applications out there. And then on the lower level, you typically see some kind of market clearing, or an economic dispatch, or something that's an energy or reserve market, or an optimal power flow, an OPF. And in terms of technical characteristics of these models, how are the technical characteristics of the power sector represented in these models? Then what I see the most is a model of representative days. Because computationally speaking, obviously we would like to model every hour in the next decade, and for our models to be able to solve, but that's so far that's not possible. So usually people use representative days to reduce the computational burden. I've seen ramping constraints on the lower level and upper and lower bounds on operations. Chronological constraints for storage, so the state of charge of storage, and DC power flows. These are some different solution methods that were out there. Now this is a slide to just give a couple of ideas of the different numerical case studies that I've seen out there. And as you can see from maybe the first three, which specifically mentioned how many variables and how many constraints that they have, then 130,000 binaries or 3 million constraints, those are not small problems. Those are large optimization problems. And solving these gets computationally very, very intensive. So we have something, you'd have to wait 72 hours in order for this model to run. Right? So if your boss really needs these results tomorrow, then that is really not a good topic to work on. Here we have some other examples of different methods and different case studies. And you'll see in general that even the most recent results don't give you results in anything that is smaller than hours. Usually either it's toy problems which solve relatively fast, okay, or it's larger systems which take several days to solve. And this is just a slide to give credit to the people who are working on this. Some of them are actually in this room or were yesterday. So there's Rentin, there is Afzal, Jean-Paul Watson, which I don't know if is here now. Yuri Dworkin, which is a magician, and he's going to solve all of our problems because I think he's published 14 papers last year only. He's my hero. And he's also very good in doing bi-level problems and DC OPF in storage, very efficient methods. There are some other applications for bi-level and storage, which I'm not going to go into more detail now because we don't have time. Okay? So now in terms of transmission and generation capacity expansion, what have I seen? Well, you can either maximize social welfare or minimize cost. You can do this from a proactive or reactive point of view. And then on the lower level, you have some kind of market equilibrium, pool-based, strategic, market clearing, or an OPF. Okay? And looking at the technical characteristics, well, how do we model power flows? Well, usually it's a DCOPF, or you can have PTDFs also, so I've seen this as well. You have 2 or 3 levels sometimes. Interestingly, I've only seen one work there with representative days. Maybe if you're aware of more, you could let me know. But in general, there is either load duration curves or hourly chronological periods, but not so much representative days. And then I've also seen, combined energy and reserve there. Different examples of different case studies and the sizes and the time it takes them to solve. But I'm not going to go into much detail here as well, because I'm going to be cut off in 10 minutes, I think, right, Chris? 10 more minutes? Yeah, okay. Okay.
It's even better if I don't have to.
Okay. Okay, so now I want to take a little bit of time of what I think is my card to Santa, what I think I would like to see in these models. So definitely one of the topics that I'm missing looking at this is, if we want to model a realistic power system and realistic power system operations, then where's the unit commitment, right? Where are the minimum up and down time constraints that we need to actually physically run our system? And I know the reason why they're not in the models is because they have binary variables, and then if you have binary variables in your lower level, then all of your convexity goes away, and then KKT doesn't work. But I think for we're in the Isaac Newton Institute, and the excuse for not using these realistic constraints cannot be that we just don't know how to do this, so we don't, right? So in the future, I would like you to find a solution to this problem and actually be able to put this into our models, because from an operational point of view, that's what we need. Another thing that I've seen is that usually if there is some kind of operation, and if there is some unit commitment, sometimes on the upper levels, then usually it's always power-based versus energy-based. And I have a co-author who works at ECN, Germán Morales España, who is very, very much in favor of power-based unit commitment as opposed to energy-based. And I'll show you a couple of results of why apparently energy-based is very, very bad. So I haven't seen any power-based applications of unit commitments. Richard O'Neill, are you here? So Richard O'Neill yesterday in his slides mentioned the OPF problem, and he mentioned the ACOPF, even though you didn't have time anymore to go into the details of the equations, but you don't see an ACOPF anywhere in these problems. Again, I know why it's not there, because ACOPF is a non-convex problem, and actually the ACOPF by itself is already so hard that you don't want to complicate your life having to put this into a bi-level problem. But then again, I think there have to be some things worked out there, or maybe in second order cone programming or something, so I think that might be an interesting direction to go into. Another thing that I think is a problem with these representative days is that usually these representative days, when you're using them, they're not linked, they're completely separate, okay? And that is good if you want to run this on a parallel computer and computationally speaking, but then there are some other things, for example, taking into account large hydro reservoirs and the operation of hydro reservoirs, where you need some kind of chronology between these days in order to model this. And you also don't model unit commitment between days. And the fact that, when you go from one representative day to another, your unit commitment at the end of the day and the beginning of the new day is linked in some respect. And then, of course, if we're going to write a card to Santa, we would also like this to be stochastic problems, if we didn't have enough problems already. Okay. In terms of the duration and capacity expansion planning problem, I've already said these, but I want to iterate that in the transmission expansion planning problem, I also haven't seen representative days, and I haven't seen a lot of storage technologies within these problems. So usually there is normal generation and maybe wind and solar, but not storage. Okay, so somebody has an idea to get rid of the loss of convexity if we use unit commitments in the lower level. somebody knows how to solve the ACOPF efficiently, well, maybe if there is somebody who combines ACOPF and unit commitment, it might be Anya. Anya Castillo at Sandia, she might save us. We might be able to go in the direction of what Hoekman and Siddiqui have been doing to solve equilibria with binary variables efficiently. And we need some very efficient numerical methods for all of this stochasticity going on. Okay, so now I don't want this talk to be completely depressing of things that I would like to be done and that currently are not being done. So I would like to use the last couple of minutes to go over some of the things that I actually have been working on in the last couple of years, and which I hope maybe might be useful for some of you in some way or another, not necessarily only in bi-level problems, but also in planning problems in general. Okay, so now I'm going to talk a little bit about this representative days business. So in general, when we have representative days, then each of these days is solved independently. And if you're doing expansion planning, for example, then these days have a specific weight in your objective function. You can model storage, for example, a battery very well because you have this hourly chronology within these days. Now, long-term storage, that's a little bit of a problem because if you have a large hydro dam and you have a hydro dam evolution over time, then how do you do this when you have independent representative days? So usually what I've seen being done is that either hydro is assumed as data, something that, you know, ex ante, you just get out of the model and subtract that from demand, for example, or that you assume a specific hydro production available for a representative day and that's it. Okay? Right, so what my PhD student Diego has been doing together with a very smart girl, Maya Domeshek, which Ben was nice enough to come over through the Wind Inspire grant, is something that we call enhanced representative periods, but I really want you to think of this as representative days pimped. Okay, so a new spin on representative days, and Richard Green has been talking about these Markov chains yesterday, I think it was. So that's a big help for me because that's going to be helping you to understand what this is all about. Okay, so imagine you have these 4 representative days, which are these 4 different boxes. And then essentially what you're doing is, if you want to approximate 1 year of operation, for example, you come up with a transition matrix and you essentially count how many times you jump from a gray day to a blue day, and from a gray day to a green day, and so on and so forth. So you count the number of times that you jump from one state, which would be the representative day, to another. Okay? Then this is the transition matrix, and you could also really view this as a probability distribution of what's the probability of jumping from a day like this to a day like that. Okay? Now, we already know that if we have these representative days, within these days, we can model batteries just fine. But what about hydro? So what I'm going to show you is that we're going to use this transition matrix between the different individual representative days to actually formulate, to bring hydro back into this model. And how do we do this? Now, this is a very simple example. Imagine that instead of an entire year, we just had 7 days that we wanted to approximate. And we approximate these 7 days with 2 representative days. Okay, so we have representative day 1, which is the blue one, and representative day 2, which is the green one. In total, 168 hours. Okay? Now, we're going to have 2 equations for storage. Okay? We're going to have one which we call intraday and one interday. Now, the intraday is what everybody knows. Essentially, it's saying, well, what I have in this hour is what I had in the previous hour, plus minus what I discharge. Okay, so that makes sense. Now, what's interesting is what we call here long-term energy storage system constraints, which essentially is establishing a chronology through a specific time frame. Okay, so I'm saying my hydro storage in hour 168, so after a week, is whatever my hydro storage energy level used to be at the beginning, plus 5 times what I charge and discharge in each of the hours of the blue representative day, plus 2 times what I charge and discharge through these 2 days. Okay? And if life continued throughout here, then for every additional storage constraint, so maybe after 2 weeks, it would be the same. Okay, so now with this, we're able to still use representative days, but somewhat link these representative days among each other with the fact that we know how they're transitioning between each other. Okay, so that's hydro. And now what we do with the unit commitment, for example. Okay, so in the same example here, this is what the transition matrix would look like. Right, so I go from a representative day 1 to a representative day 1, and I have this same jump for 4 times. This is why here you have a 4. Then from day 5 to day 6, I have 1 jump from representative day 1 to representative day 2. So this is where this 1 comes from. And 1 jump between representative days 2, which is this 1. Okay? So this transition matrix, as Richard Green has already said, doesn't need to be symmetric. Okay? And now what are we saying? We're saying in terms of the unit commitment, we can link the unit commitment in the last hour of representative day 1 with the unit commitment of the first hour of representative day 1, because we have a lot of jumps between those days. And you can say, well, if between Monday and Tuesday you repeat this exactly, then if a combined cycle unit is on here, it has to be on here. Okay, so we get back a little bit of this unit commitment chronology. And in general, this seems to be working pretty nicely, because you still have all of the computational efficiencies of the representative days, but you can model storage and you can model unit commitment. Now, you might ask what happens about the value of storage, or the water value, if you want to think of this in a hydro setting. Or can you model more complicated hydro subsystems with this? And this is some recent work that is currently under review in energy. So you could also complicate this model and use that here. As for the value of storage, each of these inter and intraday storage balances has a dual variable, and I'm not going to go into detail to show you why this is the value of water in each of these hours, but I can pass you a paper and then you can take a look. So essentially, with these 2 intra and interday storage balance constraints, we're capable of calculating an hourly value of water, or an hourly value of storage, both for batteries and for hydro, which might be an interesting thing to have. You know, if you have a hydrothermal coordination model, or maybe for investment decisions, you might be interested in that. And you can model more complicated hydro systems, but I'm not going to too much detail here with this. And now the last thing I want to mention before I finish up is some of the work that we've been doing in energy versus power, so energy-based unit commitment versus power-based unit commitment. And you see that even though this is not bi-level stuff, there is shameless self-advertisement going on here. And you can also see that how efficient PhD students become when they have to hand in their PhD thesis in a couple of weeks. So a lot of papers get written. And what we've looked at in this particular problem is unit commitment from the point of view of energy, where you essentially look at the average value of power over a period of time, or you look at the actual power of the instantaneous value that you have there. And if you just look at this particular example, where you go from 10 megawatts, you ramp up to 20, and then you ramp back down, and this is your actual operation, then if you do an energy average, this would look like a flat 15 megawatt hour. But that's not actually what's going on and what the plant has to do. And essentially what we're saying, which I'm not going to go into too much detail here, is that if you disregard what power plants actually have to do in terms of power, then you might do things that are not really feasible then in the short term, in real time. And that might be an issue if you want to assess the value of flexibility in your systems. Okay? And just to give you a little bit of an idea of how the results pan out in an application to the Dutch power system, the investment cost, if we're looking at unit commitment with investment, because we're looking at the value of flexibility, then actually if you do energy-based, you end up paying 13% more than if you did power-based. To make things worse, with the energy base, your operating cost is higher, you emit more and you curtail more. So really it seems like the power-based model gives you a lower investment in terms of capacity, but it's cleaner and more efficient. So it seems like that might be a good thing to have in mind. And computationally speaking, Germán Morales España is a wizard with making things tight and compact, so the power-based model runs even faster than the energy-based model. That's something to take into account that maybe might be useful for energy modelers in general. So what are my conclusions? And I'm only 3 minutes over, which is good because I'm Austrian and I don't like to be late. So we have seen that there are still a lot of bi-level problems, there are a lot of hierarchical problems in the electricity market, and they capture a specific insight of sequential decision making, but we shouldn't have to sacrifice all of these technical things that are going on, like the ACOPF or unit commitment, just because it makes these problems harder and we lose some kind of convexity conditions, because we want to make our models realistic and not toy problems that can be solved easily. And with that, I want to thank you all for your attention, and I would be happy to take any questions, being from the Nemesis or somebody else. Thank you.
Thank you very much. So I should just explain for the benefits of Asgeir Thomasgaard, who is acting as respondent on Sonja's talk, that we've got the sort of informal nickname for the respondents of the Nemesis. So it wasn't anything personal.
I kind of like the.
Yeah. Anyway, would you like to speak from there, or come up and come up on stage and say a few words and start the discussion?
First of all, thanks for a very nice presentation and overview. So. You shouldn't take this as a criticism against your presentation, because I really liked your presentation and the overview. I think it was very good. But being in Cambridge, it's always good to ask a question about time, I think. Mm-hmm. And for me, some of the mysteries about these, in particular, equilibriums, and you could even think that there are even more equilibriums in sequence after that. Mm-hmm. What do you get when you start adding complexity like that? Because if you look at this, if you think back to the discrete time, discrete space type of classical games, and you start elaborating those into dynamic games, you get more and more refined equilibria, and you get also a lot of theory about how you refine equilibria into what is credible and what is not credible in types of equilibria. And then when we look at the EPEC literature, a typical paper would say, and this proves that we can find an equilibrium. And there is no discussion about how credible is it that you will end up in such an equilibria. Very little discussion about how many other types of equilibria are there. And no discussion mostly about time consistency in terms of if you start out in one level of the game and you assume what will happen in the next and third. How likely is it that the players will actually behave in the way you assumed in the first place? And game refinements are very much about this question. So, for me, this is something that will be missing in the EPEC literature, is something about the credibility of the equilibria you actually find, mm-hmm. and how that will be used. And if there would be time, a follow-up question of that would be, if I as a regulator are faced policy recommendations based on such complex equilibria, wouldn't I rather try to make this a perfect competition situation and regulate away all these problems with
Okay, I'll start with your second question, because I think that's easier to answer. The first one is a very philosophical question. So in terms of the second question, I would disagree. I actually think that would I make this all a perfect competition? I would say no. Because if you always assume that your market is perfectly competitive, then you plan for an ideal world, a utopia that doesn't really exist. Because there might be market power and people might gain or withhold capacities, and then if you have some of these market failures or even market power in the market, then what might happen from a point of view of generation expansion planning, not transmission but generation expansion, might be something that is very different from what you might expect if you're a social planner and you're assuming perfect competition. So then if you're basing your transmission expansion planning, for example, on the basis of a utopian world where you expect to see that many megawatts from combined cycle and wind and solar, and then in the end you will get a lot less, then I think you might end up doing a suboptimal planning for the real world that you're in. So I think assuming perfect competition, I think is obviously that's something that you have to do because you need that benchmark. Because this is where you would like to be, but then what might happen in the real world, at least in my opinion, might be something else. And so one of the defenses that I have for bi-level programming, because as I mentioned, I haven't been working on this for a longer time, is that I think it might provide some insight into what might be going on in an imperfect world. I think today, currently, I would not suggest, a TSO actually use a bi-level transmission expansion planning model to do their planning, because I just don't think that from a computational point of view, we're somewhere where you can take every technical detail into account that you need to take into account to make these plans. So I think maybe we're still borderline toy problems in the bi-level world. But I think these problems are useful to give you an insight or of a potential plan of what might go wrong and where might be the directions where things might go wrong, and then compare the difference between that and your benchmark. So I think that's what I would answer to your second question.
That puts me also in a risky situation as I'm presenting a capacity expansion under the naive assumption about perfect competition later today. So
no, not at all, because that's what we should be doing.
Oh, but it is of course a dilemma, but somehow it's.
But you do stochastic programming, do you? Well, that's of course then you're safe.
Maybe it's the best we can hope for, and then the question would be how do you do market design regulation to get there? And my open question would be, well.
But is that the same? I mean, is that as expensive? I would conjecture that you would have to compare, because if you say, okay, I hope for the perfect world, then I see the world is not perfect, and then I put regulation in order to make the world to go where I want to be, and you sum up all of the cost of having to do that, versus imagine that there is a perfectly computationally efficient bi-level problem, which would do transmission expansion planning subject to the actual real world power market with all of its market power and its imperfections, and you would do this kind of closed loop assessment of saying, let me do the best plan for whatever it is that I'm actually going to get, and compare the cost of doing both of these things. Maybe the difference is not that high.
And that closed loop elegantly brings us back to the time consistency and
I agree. Yeah, no, I agree. So if I understand you correctly, in terms of the time consistency, it's true that these bi-level programs have an issue. So I don't know if Ramtin has showed up to kind of back me up here on the bi-level team, but no, he didn't, I see. But he had a bi-level problem with two periods yesterday. Okay, so if you have two periods and the world ends there, then that's correct. But then usually the world doesn't end there, and we know from the prisoner's dilemma that if you play this repeatedly, the outcome is very different from if you just play this as a one-shot game, and then you don't do this again. So
I wasn't planning to ask that, because as you say, then of course that brings us into repetition and signaling and all of these other things as well. So I'm probably not supposed to ask all the questions.
Yeah, well, no, I don't think we should.
No, but I think that's a very good point. I think that's a problem. That's a problem because we don't see that. We have these two stages, and then the world is over. No.
Yes, we've got time for a few questions from the floor. David.
I was really impressed with the work you're doing on representative dates. So I come from a climate science community.
It's all Diego.
So I think it's impressive the work that's going on there. I guess the question I had is, How far do you think we need to go on this? So if you picked 5 different representative days, you presumably get some different answers. If you admit there's some uncertainty in the transition matrix that you're producing, which there is, then again you would get some different answers. So I guess the question is, how far can we go on this? How far do we need to go on this? Particularly when we're also thinking against the backdrop of a changing climate. How much of a problem is this in terms of running much longer data sets?
Yeah.
These models, were those computational figures you gave how long it took? Were those for a single node, for a single processor, or is that when it's highly parallelized already? How far can we go on this?
And actually, can I just chip in a twin question, which is actually something I was discussing with, David yesterday. A different way of perspective on that would be: is there a way, or is there any work, or is there a way of working out the consequences of your simplifications for the end results without having to do a more complicated calculation, because typically you do the biggest calculation you can.
Right, exactly. So at least for the things that we've been doing, we always do experiments that we can control, right? So we have a 1-year time horizon where we can actually solve the hourly benchmark. So we have something against which to compare our results. And then we have done an exploration of how many representative days you need and how the quality of the solution alters in terms of how many representative days that you choose. And I would say that completely depends on what you're looking at. Because if you want to, for example, approximate what a hydro dam is doing, then maybe you might get away with 5 representative days, and that's fine. But then if you want to really capture storage, then maybe you need 7. And so that kind of depends on what you're looking at, what your specific study interest is. And I think if I understood you correctly, then you're saying, okay, if you have demand that changes over time, then how does this work with these representative days, and might you need more representative days in the future, and so on and so forth. And that is also well, I guess you do the best that you can with the computational time that you have available. And in general, I think that you need to, we built these representative days looking at the available data for demand, solar, hydro inflows, and wind. So that's hourly data that we have available. And then we do clustering, essentially, on those. And depending on how nasty your wind profiles or the penetration of renewables that you get, you might need more or less representative days to completely capture that. So the only intelligent or more or less intelligent answer I can give you is that you need to do a lot of studies with the actual system that you have, try out different things to get a feel for how much you actually need. So some of these papers are actually applied to a grid. So it's not some of them are on a one node system, and then some of them we actually have a little bit of a network. And of course, if you have a network, then you have more complexity and you might need more representative days. But in the end, the only actual thing from practice that I can say is that study the system that you have with the data that you have available, or with what you think might be some way in some direction to which the data might evolve, and then test how many representative days might be good for that. How much can you do computationally, and then you sit back and pray for the best. I guess I don't know if that answers your question.
I guess I still find myself slightly concerned that as someone who comes from weather and climate science community, the concept of using representative days is quite dangerous in many respects, and I think there's a whole package of uncertainty that's coming from that weather and climate space into these models that isn't really explored very well at the moment. I guess I'll just kind of probe how far.
It's like with democracy, right? You try to all of the options are bad, and you just pick democracy at the least worst, bad, I guess. If you have a better idea, then I'd love to discuss it.
Should we just take one more quick question from, I think Richard was waving. And he then de-waved. Okay, so Ben, we'll take a quick one from Ben during the changeover.
This is a quick question. I remember Herman and Andres, when they proposed the power-based model, they had a conceptual obstacle in trying to define what prices and settlements look like there. So are you now calculating market equilibria, and so you've devised a way to calculate prices and settlements in a power-based versus energy-based system?
Unfortunately,
problem's been solved?
I have to disappoint you there. This is a cost-min approach.
Okay,
so
okay,
we're doing
an open problem then.
optimal operations. It's still up for grabs in terms of if you want to send
Let's-
somebody else over
let's
for
talk over topic.
yeah, a new Wind Inspire student, so a new Charles Goulian or Maya. That would be nice. Yeah.
Okay.
You need the microphone,
Yes,
right? I'm not hogging the microphone.
Anyway, should we just thank Sonja again?